Discussing today's presentation at the Stanford Energy Seminar, Johanna Nelson Weker does research in battery technology, and she works at SLAC. So there's two big aspects to her work. One is the synchrotron, the X-ray synchrotron, which is a gigantic X-ray machine that allows for very powerful X-rays at different scales to analyze materials in situ operando, which means you can analyze a battery while it's working and you can analyze it on the battery itself. So she's doing battery research, but also X-ray technology development. So she has a physics engineering aspect and she has a material science aspect. I think really interesting. Besides the fact that the presentation itself was very illuminating and interesting, I also think, just as a side note, it's good to see that we do these types of research here, also in the United States, and particularly with respect to China and sort of taking over the world in battery technology. I think we're still here, we're still doing stuff, and actually Johanna mentioned some sort of Manhattan project for battery technology. She was talking mainly about grid storage, but in general, I think we need storage. We need battery storage because with battery storage, we can really liberate the energy grid, the energy situation. We can have a lot more flexibility in energy production and distribution, because right now the way we work is we have this centrally planned sort of from way back, Thomas Edison and Westinghouse, the kings of electricity. But what they created is this centrally planned top-down power plant with this distribution grid that always has to have a certain voltage and always have to have a certain level of amps and all that. And that's just very difficult to maintain. And we have this necessity for peaker plants, and it's just a big waste of energy. So not just that we're using bad resources, bad in a sort of environmental way, but also it's very wasteful. And I think moving towards grid storage and then transportation storage and electric transportation and electrifying pretty much everything else in the economy, I think will just really open up many new opportunities. So what Johanna's doing is working on these areas at SLAC. So I think that's really interesting. And I hope to be able to do a tour anytime soon. This is not in our podcast. It's October 23rd, 2024. This is Krim Delco. There's no update right now. Tesla just announced their earnings. So I'm going to do an update tomorrow with a discussion of the earnings call. For now, again, there's no update. So we're up 15.5%. Market's up 22.7%. We're on firm by 7.2%. So let's talk about this presentation. Johanna Nelson Weker. I think there's a couple of really interesting aspects to this presentation. Like I said in the prelude, there's battery technology research, and then there is synchrotron research. And I think like a lot of research in physics and condensed matter physics and material science, it's the subject that you actually study, and it's also sometimes the instruments that you use to study the subject. Both of these sort of work in tandem. I think a good example is all the laser technology that has been developed in the last few decades, and the ability to actually analyze, let's say, particles through lasers has been evolved because we had advances in laser technology that helped us do advances in material science, in nanotechnology, and then again we improved laser technology. And so this recursive back and forth is also happening in material science. And I think Johanna Nelson Weker is a good example of that because she's working on both. So let me talk about the battery side, and then I'll talk about the synchrotron side. So what is battery technology in general? Battery technology is applied condensed matter physics. So you have elements. In the case of the lithium-ion battery, it's lithium, and then it's there's some silicon in there sometimes, and there's some what's called doping. So you dope the materials in the battery with cobalt or nickel, and then you have graphite or even graphene, You have an anode and a cathode, and one, I don't know the details now, which one is which, and that's not so important. This is not a technical podcast. But think about it this way. Chemical energy is the kind of energy where you have electrons stored on one side of the battery, and then you can transfer them through an electrolyte to the other side by adding a charge and, in other words, plugging something in, closing a circuit, that kind of thing. And if you do that, then the electrons go from one place to the other, and then you can charge it back. That's the charging, and that's what a battery really does. It's been around for, probably more than a century. The lithium-ion battery is a little bit newer. The big breakthrough of the lithium-ion battery was that you have much higher energy density, and you have other good performing metrics such as power density, high cycle life. Those are sort of the main ones, and of course cost. So what do they all mean? So high energy densities, you can store a lot of energy in a battery. In other words, the range of an electric car can be 300-400 miles. Power density means you can get from 0 to 60 miles in 2 seconds. Like you can get a lot of power very fast. Performance means that you don't lose a lot of energy, which goes back to the range. It goes back to pretty much all the other metrics that a consumer cares about. The car is stable, the voltage is stable, your stuff works in the car, it's not flickering, things like that. And then, of course, the cost. I think everybody understands what that means. So all these metrics have to be in place. And what Johanna Nelson Weker and her team are doing is working on improving the existing battery technologies, but also working on new battery technologies. As she said, we need a Manhattan Project for batteries because there's a feeling in the industry, and I would include even Tesla with that. Like even Tesla, the market leader in electric transportation, is probably not super happy with all the battery metrics that they have, in particular the power density, because it works for cars, but how about trucks? How about even the Cybertruck? As soon as we go to very heavy vehicles and very heavy stuff, it becomes more difficult, right? So that's what I think Johanna's work is really hopefully going to yield some fruits, is that we can have batteries with 400-mile range maybe, or 300-mile range, but real 300-mile range that can move trucks and things along those lines. And by the way, there's another big one that I forgot, which is actually one of the key research projects that she presented, which is fast charging. Fast charging is probably more of a convenience factor. And as a longtime user of a Tesla, I have to attest, it's not as important as people say, because number one, you charge overnight most of the time, so you don't really care if it takes 8 or 10 hours. And when you're on a road trip, the fast charging, yes, of course, sometimes it's really important, right? The other day, we were in Los Angeles. We charged at after midnight. It was cheaper. It was a bit of a sketchy neighborhood. There were a lot of people, though, at the charging station, but it's still the kind of place you don't want to spend like 45 minutes charging. So sometimes it matters, but I would say it's not the most crucial aspect of electric transportation, simply because one of the features of electric cars, which is the overnight charging ability, is also the solution. That's and we're just used to the gas cars that we charge at the pump stations, and we want to replicate that. But I would argue that we don't have to replicate that. That there are solutions for that. But anyway, Johanna Nelson Weker is working on fast charging, and like many other of these technologies, if you solve the fast charging problem, you might be able to solve other problems too. What's the problem with fast charging? It's lithium plating. So the way I understand this is that if you charge very fast, a lot of the lithium pulverizes and gets stuck on the anode. Like when you charge, you move the electrons in form of the lithium chemicals to the anode, and then the lithium plates there, and you kind of lose you lose some of the electrons, you lose some of the capacity of the battery. Now, I'm not sure if it's because the anode gets sort of plated and then you can't, I guess you lose power density, but also energy capacity, because through the plating, you can deposit less and less material on the anode. So I guess that's the way I understand it. Again, apologies for any chemistry buffs here. or experts. This is not a technical podcast. I just want to give a sense. Think about it this way. You're depositing something on the anode, and then from the anode, when you drive, when you use the battery, it goes from the anode to the cathode, and then it goes back from the cathode to the anode when you charge. And the plating is a problem. I guess the plating just covers the anode in a way that it can't absorb more of those chemicals, and therefore its capacity degrades. So this would be the fast charging problem. And what's really great about this work in SLAC is they can do in situ operando studies, which is a fancy word for saying they can study the stuff in real time while it's doing real work. And they can study on the thing itself. So this is not some derivative simulation lab experiment. I mean, it's done in a lab, but the actual work of the battery, it's being charged and discharged as if it was real. The battery doesn't know that it's in a lab, doesn't matter, but the functioning is real, and the charges and the cycles are real, and then you can look what's happening. And here comes the other side of the coin, the Synchrotron X-ray. So you have very precise, high-power X-rays that can look at the battery, that can look at the degradation and the formations of the materials and the chemicals at very, very granular. Like she said, we go from micro to nano to angstrom scale, which just means smaller and smaller and smaller, more resolution, more resolution, more resolution. There's a couple of papers that I found on their website. She wasn't presenting this stuff, but she was talking about, let's say, software packages that help you do tomography, which means that you can take 2D images of a material and compose a 3D representation of the material. And this leads me to one of the biggest sort of exciting parts of this whole research. Again, something she didn't mention, but something that is very close to my heart, and that is simulation. So with all this data, eventually, we can create a virtual twin or a digital twin of these batteries, maybe use some sort of AlphaFold type machine learning to learn how these things behave. And then eventually, this is early days, but eventually we could have a simulation. Because what is the holy grail of all of this? It's iteration, 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 iteration. Like material science, condensed matter physics is the study of how complex materials in complex relationship with each other behave while we're doing something with them, whether it's charging or discharging or doing work. And the behavior of these things at the level of our knowledge right now, today where we stand, we are at a point where we can't really model this behavior. The mathematics that we have are not sufficient, and the AI that we have is not developed enough. Hopefully, at some point, we will get there. And I'm also very excited about quantum computing, which is simulating exactly those types of behaviors. But I'm a bit going on a tangent here, but it's important to notice that. It's important to note that we have the opportunity in the next maybe 2 or 3 decades for anybody who's now starting their undergrad or maybe doing grad work, that there is a potential to solve these types of problems. So battery degradation can be studied in virtual space through simulation, and then we could iterate much faster. Of course, this is a little bit science fiction now, but I just wanted to mention this because it shows where this work is going, right? Or in other words, we're all sitting here saying, well, when can we simulate all this stuff? And the answer is, listen, first and foremost, we have to have the technology that can see what's going on in the first place. And once we see what's going on, we can model what's going on, and we can maybe collect the data and use machine learning and AI models to then simulate the behavior of, let's say, a lithium-ion battery or other materials, which is another part of Johanna's research. It's working on other materials. So to summarize, this is a great example of a seminar that I think is very useful. We're going around Stanford doing seminars and lectures and interviews. It is like always a little bit like looking for gold nuggets, right? There is, even at Stanford, a lot of dirt that you have to dig up to find gold nuggets. This is one of those. I think Johanna is a very concise, very clear, very Occam's razor type person. She doesn't use a lot of jargon. She's down to earth. Her work seems to have purpose. The way she presents it, I can see the purpose as a long-term renewable energy investor. This is important stuff. We need storage, we need better materials, and we need better technologies to iterate faster around those materials. And all of these things are combined in Johanna's research. So I encourage people to go to her website, or as she said, maybe even do a tour at SLAC. Thank you.